the organizers, of course, for inviting me. So I've learned several things at this conference, and one of them is that Martin Bridson and I have a serious difference in theology, in that he believes in... Well, no, I mean, he seems to have an idea that gods have created mathematics, and I'm much more pessimistic. I think mathematics was created by gods and demons. And so in particular, the problem I'm going to talk about today, sort of simply described, is I'd like to ask about the finitely generated subgroups of infinite index in SL3Z. And anybody who's worked with this group knows that it is actually the work of a monster and not of a god. So one way of interpreting my talk is that it's a description of the battle between the forces of good as embodied by me and the forces of evil as embodied by this group. And, well, okay, that's exactly what I was going to say. The outcome is not happy. As always, the forces of evil will win at the end. But that's, yeah, I mean, this is a little microcosm of life. I should also thank Professor Laborie for introducing me to some new French words as well, as part of them. So there are some trivial examples, of course, of subgroups of infinite index in SL3Z. And, well, the most trivial, of course, is finite groups. They'll play no role at all in what I'm talking about here. Slightly less trivial, of course, is the notion of free groups in SL3Z, and we know from TEATS that you can construct these very easily. So if you take any non-soluble subgroup of a linear group and you just take a couple of random elements that power them up, probably they're going to generate a free group. So free groups aren't going to be so interesting from the point of view of what I'm talking about here, although they aren't completely trivial. A more interesting and, well, really highly non-trivial example, but still not so interesting from the point of view that I'd like to articulate, is described as this sort of example here, that you can actually get surface groups inside SL3Z. And I've given you a brief description of a construction, although I won't justify, there's some pretty nice mathematics that lies behind this. But if you take a 3x3 integer matrix, which is symmetric and has the appropriate signature, then you can ask yourself about the collection of matrices for which it's an isometry of that form. So this is what's usually called SOQ, and I'm just looking at the integer points here. And then some very high-powered mathematics tells you that actually this contains a surface group with finite index. And the surface group may or may not, in fact, be a closed surface group. In fact, it's always the fundamental group of a surface of finite area, but you can tell exactly when it's a closed surface group, actually. It's a closed surface group if and only if there are no integer light-like vectors. So if you write down a diagonal form, for example, something like x squared plus y squared minus 3z squared, then it's easy to convince yourself there are no integer solutions to that form being 0. And so the group that I've just written down here will actually give you will find for you a closed surface group inside SL3Z. Now, I'm not quite so interested in these because they aren't Zariski dense. I'm more interested in something which is actually Zariski dense in SL3Z. So let me say something about that. So a good way to actually try and construct surface groups is to think about triangle groups. So let me briefly remind you about a triangle group. Triangle groups are two generated groups, and for any triple of integers, p, q, and r, you can make yourself a triangle group, and it's very simply presented in the fashion I just described. And then triangle groups fall into various types, And we're interested in triangle groups which should give us subgroups of finite index, which are hyperbolic surfaces. And the condition for that is basically the orbifold Euler characteristic. So the Euler characteristic here, these guys have torsion, obviously. And if you unwind what the condition is, the condition that there's a surface of genus greater than or equal to 2 of finite index is exactly that condition. Now, if you're trying to find a triangle group and put it into SL3Z, then it's pretty clear just by thinking about the characteristic polynomial of the matrices in question that the torsion is very restricted. If you're to have a finite order for a matrix that lives inside SL3Z, then the order has to be either 2, 3, 4, 6, or infinity. And in infinity, you have to say a little bit more about, and maybe I'll say that in a second, but these are clearly the restrictions on P, Q, and R that you need. And then you need this condition as well in order to get this thing to be negatively curved. And so it turns out that one can actually show, for example, one can do a little bit more than this, which I'll describe on the next slide. But this is joint work with Alan Reed and Moore and Thistlethwaite, that you can actually find a discrete faithful Zariski dense family of representations of the triangle group 3, 3, 4. And it turns out to be very simple. So as I've described them, of course, they're representations into SL3R. But the polynomials here, of course, these are integer polynomials in a variable t. And in fact, the way this is constructed, for any real value of the parameter r, these are, in fact, discrete faithful representations of this triangle group. And so if you take an integer specialization, any integer you like, then, in fact, you get a representation into SL3Z of these triangle groups. And, well, they're all Zariski dense. Maybe I'll defer talking about exactly why they're Zariski dense for a second. But if they weren't Zariski dense, well, it's pretty easy to convince yourself they're Zariski dense. And I'll say something more about it later on. At any rate, this is a very simple and elegant way of constructing a one-parameter family of representations in SL3R, and all the integer points are actually discrete faithful. All the points are actually discrete faithful representations of this triangle group. And maybe, I think maybe this is actually already mildly interesting in the sense that this is the first example I know of sort of infinite families of these kinds of representations of groups into any sort of group, in fact. One knows from many situations where you try and find representations of surface groups, there are often only finitely many of them up to conjugacy. And actually, these guys are all different. And they're all different even up to commensurability in SL3R. So actually, you get an infinite family of Zariski dense surface groups, none of which are commensurable, in fact. So let me tell you something about why such a thing might be true. And this uses, a good way to think about this is to think about this in terms of real projective structures. So, I'm sorry? I'm sorry, maybe, I think that there's Zariski dense actually for every value of t. So sorry, maybe I said the wrong thing. Yeah, for every value of t, these are actually Zariski dense. Yeah, I'm going to draw a picture shortly which sort of shows how this works out, and I'll describe something about it. But these are actually Zariski dense for every value of t, in fact. So the way these guys are made actually is sort of uses a technique which I kind of like to construct representations, which I'll sort of try and fit into this slide here, which, and the reason they're discrete and faithful is because of beautiful work of other people. So one actually starts out with a representation which one knows one has, actually which lives in SO21. Namely, we know that the 3, 3, 4 triangle group is hyperbolic, and so there actually is an essentially unique representation into SO21 of this group. Now, Goldman and Choi proved, I think quite a long time ago now, maybe even in the last century, that In fact, there's a two-dimensional space of deformations of these guys. If you look at the representations in the SL3R, I think they fall into three components. And in particular, if you look at the component that contains this one, this has come up a few times in this conference, which justifies me talking about it here, there's a component called the Hitchin component, and all the representations on this component are actually discrete faithful representations. So the strategy for proving, for finding these representations is to compute that component or compute the representations exactly. And it turns out that there's quite a good technique for doing this, which I worked out a few years back with Darrell Cooper and Moore and Thistlethwaite. And you can actually figure out what this representation looks like completely. And it's not very complicated, in fact. You know there are going to be two real parameters, and then there's one piece of complication that comes from taking the square root of a homogeneous polynomial in those two parameters. And actually that gives you all the representations. And it's only because I was too lazy to write it out that I didn't actually write out the two matrices. But you can write out the two matrices quite simply. There's quite a lot of work in figuring the variety out, but when you get it, it turns out to be rather easy. And then you can actually just use some Diophantine analysis on the component that contains the original discrete faithful representation to figure out one-parameter families of representations which have coefficients as being integral polynomials. So this part's very simple-minded indeed. You just do something very simple-minded, and you can find one-parameter families which lie inside the Hitchin component so that the integer points all lie inside SL3Z. And so in this way, you can make infinitely many families. And so in fact, you can make many other such families for 334 as well. So in 334, I don't know how to do Diophantine analysis on two-dimensional varieties, but you can sort of pick out various other kinds of families. And so in particular, the family I wrote down is just the simplest one. And there are other families as well for this particular triangle group. I should also say that Bill Goldman pointed out to me that he had an example of this where he started out with, something that I don't understand very much about, some Katz-Winberg thing. And he actually pointed out that you could use that to make a representation of a surface group. In fact, also 334 into SL3Z. But it's my understanding from talking to him, I mean, I asked him this explicitly, that this Katz-Winberg idea would only find you a finite number of representations up to conjugacy. So the fact that these guys are all different seems to actually go well beyond that. And you could also use the same method to try all the other guys that you might want to try. So in particular, if you look at all the other, I'm not sure, I put etc. here in case I forgot everything, which I think I did actually. All of these triangle groups have this kind of behavior. And I should say something about what infinity means here. If you look at deformations here in the real, starting out with the hyperbolic surface, you should keep the cusp unipotent in order for the real projective structure to remain something of finite volume. But if you do that, everything else goes through as before. And so all the triangle groups that could possibly have representations into SL3Z, it turns out that they all have one-parameter families, and maybe very many one-parameter families, which are all distinct up to conjugacy. What's that now? Well, getting a two-parameter, I mean, there is a two-parameter family into SL3R. But I mean, as far as I know, that I can only see how to pick out a one-parameter family in SL3R, which has integer points on it. That's all. So no, I mean, the picture is just very complicated. I don't understand how to assemble all those points together, but maybe you could. It looks as though there are sort of some sporadic points that occur for low values of T. So the rough picture, just to sort of summarize what I've talked about here, is there's a certain quadratic polynomial is homogeneous where if you figure out the representation variety, so if you like the deformations of the real projective structures, the complete representation lies here. That actually has to lie in the place where the discriminant locus is actually 0. And then you get these components. It looks from this picture, you have two real parameters as though this is actually a disk. But in fact, there are two choices of square root. So actually, this assembles to be, over each UV point here, you get two representations depending on which value of the square root you decided to take. And then over here is another component where, well, to pursue the theological theme, this is where the demons hang out. There are actually one-parameter families of SL3Z representations over here as well, but God only knows whether they're faithful or not. So here we had to use things to do with the hitching component to be sure that the representations are actually faithful. And then this point here that's sort of drawn in blue, that's Bill Goldman's point. And there's a whole sort of SL3R family of representations that go through there. And then there's a whole bunch of other stuff here, which I haven't bothered to put on the picture. And you can actually use this. In fact, Richard Schwartz has looked at complex hyperbolic representations of these groups. And those lie along this green line here. So in this green line, actually, you can see how to make these representations actually live in as isometries of a complex hyperbolic space. But the discreteness picture along here is a lot more complicated. Just for general reasons, it has to be discrete for a little interval along the green line. And then there's some sort of spectrum that we don't really understand. There's one question that sort of arises out of this, which I thought was kind of interesting. Can you find a representation of a surface group in SL3Z which has no Fuchsian element? So all the Zariski dense ones you get, all the representations you get which are arithmetic, they'll of course, they are secretly representations of Fuchsian groups. But actually all the Zariski dense ones we make here all seem to have Fuchsian elements in them as well, at least for the triangle group. So it's easy to see for a triangle group that if one of P, Q, or R is even, then there is an element which actually has, maybe I should clarify. What I mean by a Fuchsian element here is something that looks as though it might have lived in SO21. In other words, there is a 1 eigenvalue. And it's easy to see if one of P or Q or R is even, then there is an element which has a 1 eigenvalue over the whole representation variety. And so in particular for all the SL3Z representations. So this is kind of an interesting question because although I don't see the comparison as compelling, people are interested in the question of whether you can find surface groups represented into mapping class groups in a way so that all the non-trivial elements are pseudo-Nosov. And it's perhaps a plausible kind of warm-up to ask yourself whether you can do something like this, maybe in the context even of SL3R. So in fact, I put this in so that nobody could actually do it by the end of the talk. But you can ask yourself, in fact, whether there are SL3R representations of surface groups for which there are for which no element is Fuchsian. And I think that would be kind of interesting. So in particular, you can take one of these triangle groups, pass to a subgroup of finite index, and then the deformation space is much larger. And so maybe you could actually deform it there. But I'd like to see one explicitly. So surface groups wasn't so bad. So let's move up a dimension. Here's the question which actually originally motivated my thinking about these sorts of things. Can you find a faithful representation of a 3-manifold group in SL3Z where, let's assume it's a finite volume hyperbolic 3-manifold group. So I think I'm interested if it's compact or finite volume. Either of those would be interesting. And the reason that I sort of got interested in this was because of a question that was raised by Sarah about SL3Z. Namely, does SL3Z have the finitely generated intersection property? That is to say, if I give you two finitely generated subgroups, does their intersection have to have finite, is their intersection finitely generated? Well, what should I say about this to start with before I take this slide up? Well, one thing is that when I first thought about this, actually, I really believed it was going to be pretty much impossible. And I spent quite a lot of time trying to prove that you couldn't really have very many interesting representations at all. And the jury's still out, actually. But I conjecture now that, in fact, probably most hyperbolic three-manifold groups have such representations. And the question is whether you can get anything more out of it than I've said. So if the answer to this question is yes, then actually the answer to Sayre's question is almost certainly no. And I've only put in almost certainly because there's a conjecture in three-manifold theory that says maybe every closed hyperbolic three-manifold, or maybe every hyperbolic, finite volume hyperbolic three-manifold should have a finite sheeted covering which fibers over the circle. And everybody believes that to be true now, I think, but it's not known in general. So maybe you're unlucky. Maybe you actually happen to find a faithful representation of somebody that didn't have a finite sheeted covering over the circle. But you shouldn't be depressed about that, because although you haven't answered Sayre's question, you've answered a question that was raised by Thurston. So one way or the other, you've answered somebody really rather good's question if you can do this. So anyway, let's pretend that you're more interested in answering Sayre's question. Then let's assume if I give you a finite, a faithful representation of the fundamental group of a three-manifold, that you pass to a subgroup of finite index which fibers over the circle. And so you have this short exact sequence. And then you can easily, from this short exact sequence, construct a subgroup of finite index, construct a counterexample to Sayre's question. So I've just outlined that here on the grounds that one should prove at least one thing in a talk. And so this is the thing that I'm proving. So if you take somebody in the fiber group and somebody who represents the stable letter, then just, for example, because of Tietz, you can power up the element of the fiber group and take it with the element of the stable letter so that you see a free group of rank 2. So that's easy. And now the intersection of that free group of rank 2 with the fiber group, in fact, is a counterexample to Sayre's question. The point being it's non-trivially normal inside a free group of rank 2, namely the free group of rank 2 that we first thought of. It's normal because this fiber group is normal in the three-manifold group. On the other hand, it has infinite index. And so the fact it has infinite index just follows because we have a faithful representation of this group. And so this element T doesn't power into the fiber group. And the only reason for sort of mentioning this in this sort of detail is to say that actually to resolve Sayre's question in the negative, you don't really need a faithful representation of the three-manifold group. You only need a representation where the image of the stable letter doesn't power into the image of the fiber group. So faithfulness isn't actually necessary. And, well, maybe that's useful and maybe it isn't. It's certainly, well, it turns out it wasn't useful to me. But, and I should also mention, although this is even sort of more speculative, that if you knew that you had such a representation and you knew a tiny bit more, in the interest of scholarship, I should mention that perhaps the coherence question is more interesting. So Sayre also asked whether finitely generated subgroups are finitely presented. And I'll just say something vague about this, that this is, if you had a faithful representation of a finite volume three-manifold group, you'd be fairly close to doing this. You'd need to know a tiny bit more about the image than just random generalities in the way that I did with the finitely generated intersection property, but it would be pretty close. So representing three-manifold groups into something like SL3Z or maybe even SL3R to start with is a kind of useful thing to do. So as I said, I first heard about this question, I was interested in it, and I thought there was just no way you could do this for even the figure-8 knot group. And so, well, it turns out that you can. And so I'll just sort of sketch to you how you can actually construct rather a lot of representations of the figure-8 knot group into SL3Z. So it's in the spirit of the surface group case, but one of the difficulties, although it isn't really a difficulty, is you need a representation to start off with. So this is a presentation for the figure 8 knot group, and this presentation is I presented it as a 3-generator group, but it's of course a 2-generator group. The stable letter and T will suffice, but I like to think about it like this in this context because X and Y generate the fiber group, and knowing things about the fiber group turns out to be what you'd most like to do. So there are various ways to try and make 3-dimensional representations of the figure 8 knot group into, let's say, SL3R. And then we'll apply this technique that I talked about previously and look for the integral points. And, well, there are other ways to do it than this, but actually this, I think, is a rather elegant way to do it. You start out with a representation of the group into a finite group, and then it turns out you can use Hensel's lemma to lift it from a representation of SL3 into, with the field of 3 elements up to SL3 where the coefficients are in the p-adics, and in this case the 3-adics. And then if you do it correctly, actually you can find out using a sort of a p-adic version of the LLL algorithm that you can arrange that the character lives in Z. And from that, you can actually find for yourself a representation of this group into SL3Z. And the representation you get is already quite interesting, actually, as I'll explain shortly. But then once you have that representation, you can apply this other machine, and it turns out that the dimension you expect is 2-dimensional. And so, in fact, you can get a 2-dimensional family of representations of this group into SL3R. And yeah, no, exactly. You have to, yeah. In general, you have to be quite careful about how you do it. You can go very wrong, of course, but it's important not to do that. So, you know, the way mathematicians use the word by hand these days is a little by hand with, you know, this sort of machine sitting next to me. Yeah, no, that's so yeah. Yes, with a few primitive tools, one can do it by hand. Yes. And this representation, again, I mean, one of the things that comes out of this is that these representation varieties aren't so bad. You end up with something that's a biquadratic extension of a field of transcendence degree 2 over Q. So, I mean, it's not terribly pleasant. You do need a computer to do anything meaningful with it. But in the grand scheme of things, it is not unbelievably disastrous. So it turns out that looking for integer points on here is something you can do quite effectively, and you end up with 2 families of representations of the figure 8 knot group into SL3R. So in the same way as I described previously, each of these guys has a parameter. They both lie in SL3R. That you're allowed to choose the parameter to be anything real that you would like. And then you take any integer specialization of the parameter, and you end up with representations into SL3Z. And the only one, in fact, that's degenerate is if you take t equals 0 in this second family, then you end up with a finite representation. But other than that, these representations are irreducible except for a very small number of values of the parameters. And, well, I mean, there are 2 questions you can ask about them. One is you can ask whether any of them is faithful, or you can ask a sort of this more relevant question, perhaps, whether actually what you have is representations which have the property that the stable letter doesn't power into the fiber group. I should say, in the interest of completeness, perhaps, that we're able to show, I mean, maybe this sort of summarizes some of what I've described previously here, that these representations are irreducible except for a very small number of values of the parameters. And in fact, there's a risky dense for all integral specializations except for 0. So as I said, for 0 you get a finite group, and so that's not interesting. But otherwise, they're all Zariski dense representations, even on the fiber group, in fact. I mean, that was sort of forced, in fact. So you have Zariski dense representations into SL3R, and they fall into two kinds of families. And, well, since proving things as Zariski dense isn't always so easy, let me just say something about how that was done. It turns out to be fairly simple-minded, but it turns out that one can prove Zariski denseness in a fairly brutal way for representations into 3x3 matrices. So Alan Reed and I proved the following very simple theorem, that if you have a finitely generated non-soluble subgroup of SL3Z, and you can find any element at all whose characteristic polynomial is Z-irreducible and non-cyclotomic, then in fact, if you take the reduction of this group modulo P, it subjects for infinitely many values of P. So once you have that, you can take that with a theorem of Lebotsky that says, well, actually, you only needed to subject once to be Zariski dense. So these two things taken together tell you that a very simple computation here shows that these guys are all Zariski dense. And actually, this has a sort of independently interesting corollary, I think, that actually SL3, the figure 8 knot group subjects SL3P for all but finitely many values of P. So once you know a group is Zariski dense, strong approximation tells you that it's actually congruence dense. And so that tells you that these guys, it has to subject actually for all but finitely many values of P. And one of the reasons that that's mildly interesting is one knows from work of Lebotsky that the figure 8 knot group has many non-congruent subgroups, but actually finding such subgroups isn't so easy. And this actually finds for you an infinite family of these guys. It's some fairly baby group theory to convince yourself that actually these, the kernels of these homomorphisms can't be congruent subgroups. So this is an infinite family of non-congruent subgroups in the figure 8 knot group. So we knew they were there, but we had never seen any. Or, right, exactly. Yeah, no, exactly. No, exactly. I mean, well, yeah, I mean, this is one of the reasons for pointing this out. Showing things as Zariski dense in general is very hard. So this is very special to what happens in dimension 3, that's all. It's very much brute force and ignorance. So these two families, I find this, maybe I'll put this back here for a second. So, I mean, these two families, they look very different, and they seem to behave very differently. And in fact, this one is much wilder than this one for reasons that seem hard to understand. And in particular, if you fool around with these things for a while, I mean, an obvious thing to do, for example, it's not difficult to convince yourself that one of the reasons the figure 8 knot group is a good group to think about is that the fiber is a free group of rank 2. So if you could somehow show that the image of the fiber group was a free group of rank 2, then free groups are Hopfian, and then you would know that actually the representation was faithful on the fiber group. And once you know it's faithful on the fiber group, that tells you it's faithful on the whole group. And so, you know, by hand, what you check is words of length less than or equal to 16 in this group, and you discover that the number of words of length 16 in the fiber group is the same as the number of words of length less than or equal to 16 in the image group. So that means that there is no relation in here of length less than or equal to 32. And well, the news is not good in that sense, that it turns out that in the beta family, actually, there is a relation of length exactly equal to 32, which is just bad luck. And in fact, after thinking about it a bit, it turns out that you can show that for the beta family, actually all of those images have finite index in SL3Z. So that's a little disappointing, but I did tell you that the forces of evil were going to win, and this is the first sign of them massing on the borders. This guy has finite index, and on the other hand, it's not difficult to convince yourself that the images of these guys, actually it's slightly difficult, but I mean the images of these guys actually intersect in a single element. So the proof of the first fact is actually non-explicit in the sense that there's a result of Venkataramana. I actually practiced this before, sorry. Venkataramanan, that in fact, if you can find certain sorts of rank 1 parabolics, then the images of any Zariski dense subgroup which contains this rank 1 parabolic together with an element that commutes with it will force any Zariski dense subgroup that contains this to be finite index. So actually, if you fool around with these groups, then in fact you can't find these rank 1 parabolics at all, and so you're actually quite cheered up that it won't have finite index, because if it has finite index, it has to have such people. But in fact, once you start being a bit smarter about how you look for these things, in fact, you can find these rank 1 parabolics that you require here in order to generate this abelian subgroup that's needed to apply this result. So it turns out they're quite long, but you can actually find them. They both have length 16 or something in the generators. So that shows that these guys have finite index, and it's not so hard to see that the intersection of these kernels has at most 4 elements. So that's not so bad, but it turns out that ruling those 4 elements out is pretty difficult. And I'm not going to say anything about that, but still, it's sort of satisfying that you can rule them out. I should say that you don't know what the index of these guys is. This proof doesn't actually tell you much about what the index is, but it's just really big. So even for very simple examples here, you can actually estimate the index, and that's actually an interesting story on its own, but I'm not going to say much about it. But you can estimate the index in the sense that you can find numbers that it's divisible by. And so in particular, if you take t equals 7, for example, then it's divisible by this ridiculous number here. And the growth rate of those numbers is gigantic. So it's sort of interesting. I mean, this is one of the incarnations of the fact that SL3Z is just a very bad group indeed, that you can write down 2 very simple-looking matrices, and they will generate a subgroup of finite index, and the index is gigantic. And in particular, this was of interest to us because Lubotsky asked some question about whether, if you take the profinite topology on SL3Z, can you actually find arbitrarily small 2-generator subgroups which are very close to the identity? So, in other words, if you look at some congruence kernel, so some map of SLNZ down to SLNZ mod P, can you find 2-generator subgroups inside those kernels? And unfortunately, this doesn't quite do that. What this shows is you can do it with a 5-generator subgroup, which is perhaps less interesting than 2. But this shows you can actually find very small subgroups, at least in a very small neighborhood of the Klein 4 group. So I think Lubotsky's question is still open. I think it's known to be true that you can find arbitrarily small 3-generator finite index subgroups. But I think the question about 2-generator subgroups is still open. So the fiber group here is very small, but it doesn't quite lie inside a neighborhood of the identity. It lies inside a neighborhood of the Klein 4 group. So the row family is a bit more promising in the sense that it doesn't seem to have any structure to it at all, which in my, I've been worn down by the forces of evil. So the fact that there's no structure I regard as a sign that maybe there's some light at the end of the tunnel. It turns out that guy has finite index for those 5 values there. In particular, for k equals 1, we don't know what happens. And if you know anything about the figure 8 knot group, you'll know that k equals 1 is a special value here, so you should expect it to behave differently. So, and it uses the same sorts of ideas previously, but in a way that's much more uncontrollable, in the sense that when we were able to do it for the beta family, there's a particular pair of parabolics that you can write down which exhibit the group as a subgroup of finite index. And in this case, there seems to be no such structure. The techniques that applied previously just don't seem to work. So there's some hope that these groups are worse, although the forces of evil being what they are, maybe that's just a ridiculous optimism. In particular, the indices are much worse as well. So if you take even k equals 5 here, then the index is much, much bigger. And I mean, those two matrices are very innocuous matrices indeed, but they still manage to somehow generate a subgroup of finite index. In particular, you might ask about the comparison with a free group that I described previously. For k equals 4, the shortest relation seems to have length 116. I mean, this is just a very unhealthy state of affairs. So in particular, the obvious question then is rho k faithful for any k greater than or equal to 6? And I have no idea. Seems no reason to believe it might be true. But at any rate, it would be interesting to understand whether or not the subgroups of finite index you generate in this way have any kind of good structure to them in the way that the beta family did. Of course, as I said, to disprove Sayre's conjecture, you don't really need this guy to be faithful. It's enough to know that the index of the fiber group inside the figure 8 knot group is infinite. If you could ever show that there was a value of k so that the stable letter didn't power into the fiber group, that would actually be enough to deal with Sayre's conjecture. And there are obstructions to what can happen here, which are strong enough to show that this can't happen in a uniform way. So as you look at this family and you let k go to infinity, the lim sup of the powers that are involved is infinite. But it seems very hard to rule out the possibility that any particular representation has its stable letter not powering into T. And so, you know, especially on the last day, well, but for the triangle group, I claim to have analyzed the situation completely. For the triangle group, I claim to have analyzed the situation completely. So the representations I wrote down are a complete set of representations for the triangle group into SL3R. The situation for the figure 8 knot is a bit more complicated in the sense that I started with a particular representation and then I somehow extrapolated from that this two-dimensional variety. So of course, I mean, let's see. So the figure 8 knot group has a three-dimensional representation coming from the Bureau representation. So the four-strand Bureau representation, the representation of the four-strand braid group gives you a three-dimensional representation of the figure 8 knot group. Now, what I've never checked, because it's sufficiently messy to do so, is whether if you start out with one of those representations and extrapolate that you get other interesting representations in SL3Z. In other words, I don't know that the two-dimensional variety I've constructed is actually all representation of the figure 8 knot group. But some of that doesn't seem to be where the difficulty lies. I mean, I think, like I say, I think my picture is that, in fact, many hyperbolic three-manifold, I mean, a year ago I wouldn't have believed this, but now actually I believe many hyperbolic three-manifold groups have large and interesting representations in SL3Z. The difficulty is the absence of any tool to deal with those representations after the fact. And, you know, either you end up in the situation which you don't like or you just don't know. So k equals 6 is a group with very specific small matrices. And, you know, what you do, I don't know. Well, okay. Well, these involve parameters. So actually, I claim that that is in fact all the representations in SL3C that you can get, which come from extrapolating this thing you constructed by Hensel's lemma. And there might be other components of this. I don't know, but there comes a point where, well, the forces of evil always win.